Okay, hello. I'm here to talk about Stream Fusion, but I'm just going to get right into it. So here's the basic problem. Writing loops, especially when they get big, is hard, annoying, hard to get correct, and not composable. So I think sort of the thing you would like to be able to do is say, write all the component parts of the loops separately and then compose them together. So you have lots of small modular pieces that you can use. However, and in the purely functional programming community, we normally talk about it as stream processing. However, there's a problem with this. When you implement this naively, you end up consing a lot. You can see here the first. This is really simple, and the compiler might get it. But you can sort of see the issue. Each mapcar invocation will allocate a new list. But you can see that as long as we're talking about an immutable sequence, we should be able to fuse this so that this entire operation happens in a single pass. But as long as there's a reference to the intermediate list, this is actually impossible to do. So here's one way to solve this. We can use multi-stage programming. I wrote a library based on a paper that's actually written using meta-OCaml, which I ported to Common Lisp. Meta-OCaml is an extension to the OCaml programming language that adds type-safe code generation. We remove the types, and it turns out you can implement this in vanilla Common Lisp because we have access to the compiler at runtime. You can see here, the way this sort of works is we build up this sequence data structure. It's like a graph, kind of like in Hasig's talk. And at the end, we generate some code and then compile it and run it. Here's an example of what the code might look like. There's everything here is a function except for fn, which is a macro, but it's really just syntax sugar for wrapping a lambda expression inside make instance. So, and it's not actually fundamental. It's just there for dispatching purposes. And we can see this is the code that gets generated. You can see that it ends up becoming this pretty nasty looking, but probably you wouldn't write this by hand, loop that theoretically should give you pretty much optimal results. All the intermediate parts of the pipeline get removed, and basically things are good. And this scales pretty well. Here are the references for this. There's a paper. There's actually a new paper that came out 2 years ago that extends this a bit further. I have not used this, but it can actually, it gets slightly better theoretical guarantees with, I think, making some more assumptions. For this implementation, works for any data types on any kind of stream, but the new one that these people are working on, I think, uses some compile time code evaluation. So it has to know the data types in advance. And I'll stop here.